Okay, so 2022 deferred question 10. This is page 331 in your papers. So Mark adds some horizontal and vertical grid lines and shades in some of the resulting triangles. The diagram on the right shows the pattern that he makes in the square for which x is between 0 and 1 inclusive and y is between 0 and 1 inclusive. So really, when you're marking in the coordinates here, you can see why it's 0, 0, 1, 0. This would actually be 1, 1 because you're going over 1, up 1. What percentage of the square is shaded? Well, it's 50%, half of it, because you can see it's symmetrical. Like he's symmetrical to him, he's symmetrical to him, and he's symmetrical to him. So if they're all equal, then, like if you imagine they're doing axial symmetry across here, it would definitely be 50% is shaded. Okay, the diagram below shows the same square. Mark draws a vertical line through this square at x equals k. So this, all vertical lines are x equals to something. So anything that goes down the page is x equals to something. We know it says that k is bigger than halfway and less than 1. So the halfway point, so let's try and put in some coordinates here. So a, for example, would be k something. This would be k something. This is k something. This would be k something, and this would be k something. So each of those would have to be k something. For example, this one is the halfway. No, sorry, this would be 1 and then halfway. This would be 0 0.5, 0 0.5. This is 1, 1. So actually that makes that makes h k1 actually, because you're going the whole way up. And actually this is k0. So we have quite a lot of points there. And actually this is 0 0.5 because you're halfway up at that stage. So what's the question? So there is one triangle in this diagram that must be congruent to T. State what triangle this is and prove the triangle is congruent to T. So I think it's pretty obvious, I hope it is to you guys, that the only triangle that looks the same really as T is the pink one there that I've highlighted. So we're going to say that triangle HFG. So the triangle HFG is congruent, and now we're going to have to prove that. So the tests of congruency are RHS, SAS, SSS, or ASA. So we have to do one of them. So let's just mark out a few things. So they both have a right angle anyway. So that might be a good place to start. So the measure of the angle GHF is equal to the measure of the angle CAB. And what we can say is that they're both 90. They're both 90 degrees. Now, the other thing that's definitely going to be the same is, if you look at where the green highlighter is here, they have to be the same, those two sides. So we're saying that the distance from A to B is equal to the distance from H to G. Why is that? Well, if you think about it, really, this whole thing is like a giant rectangle. So opposite sides in a rectangle are the same. So they are opposite sides in a rectangle. So there actually are going to be the same. And then we only really need one other thing. The thing that's kind of popping out to me is the alternate angles. So I'm thinking, like, if we look at this as an alternate angle, it would suggest there that that angle on the top right, so this one, should be the same as this one. But then that is ultimately the same as that one because that's an isosceles there, triangle. So we can also say that the measure of the angle HGF is equal to the measure of the angle ABC. So ABC is the same as HGF. And the reason for that was the alternate and isosceles. Now that's us done then, because we have now shown that the triangle GHF is congruent to the triangle ABC, And we've proven it by angle, side, angle. So that is the congruency part done. So that's that bit there. Now, what else? Find the coordinates of C. Give your answer in terms of K. So the coordinates of C. Well, we know that C is definitely K something. And I guess I'm also thinking here, like we already have that bottom bit, that bottom line there that I highlighted in green. I mean, if you think about the full length over is 1, so 1 minus K would be that line. But because this one's the same, that's also 1 minus K. So the coordinates of C can be written as K and 1 minus K. And then finally, show that within this square exactly half of the line K equals K passes through shaded triangles. So, well, straight away we can see that because we already said T and the pink one are congruent, well, then we automatically know, so we better just write it down, but we automatically know that H to F is the same as A to C. So H to F should be the same as A to C. And the reason is because they're congruent triangles. We've already said that. Now, what else do we know? So we know that, so F to H and A to C, that's what we have there. F to H and A to C, yeah. Now, we also know that if we add them all up, so in other words, if we do A to C, C to D, D to F, and F to H, in total, it should add to 1. So H, F, and FD. So H to F added on to FD, added on to the distance from D to C, added on to the distance from C to A, should add to 1 unit because it's 1 long. And if we know that H and F and A and C are the same as each other, so you could replace essentially that in there as well. So that would be an AC or CA. DC and CA. So there's now really 2 of them. So if we've 2 ACs and then 2 others equals to 1, well, then we essentially can say that F, the length from F to D plus D to C should be equal to 1 minus the 2 ACs. So basically, you're saying that the last 2 remaining, F to D and D to C, if they're also the same, then that's like saying FD plus F to D equals 1 minus 2 AC, and 2 FDs equals to 1 minus 2 ACs. Well, that makes sense, doesn't it? Or you could cancel the 2's even. Or you could even say, if you bring them back over, if you want, 2 FDs and 2 ACs is equal to 1, which would mean an F and a D and an A and a C should be equals to 2 times them is equal to 1. So if they were on their own, in other words, if you move the 2 over, you would indeed get a half. So the measure from FD and AC, so FD and AC, the 2 shaded ones, is exactly half. That is another one done.